You ever stop and think about all the stuff that's left over from farming? The shells, the husks, all of that? Most of it just gets thrown away, right? It's just waste. But what if hidden inside all that agricultural junk is a massive, untapped source of energy? Well, today, we're going to put on our lab coats and do a little scientific investigating. We're going to see if we can crack the code and turn all that waste into watts.
So, here's the deal. On one side, we've got literal mountains of biomass. We're talking palm shells, rice husks, you name it, just piling up. And on the other side, we have a planet that is absolutely starving for new, cleaner ways to get energy. You see where this is going, right? It feels like a perfect match just waiting to happen.
But, how do you actually do it? How do you take a big pile of palm shells and turn it into something that can power our lives and do it efficiently? That's the real question here. And it's a challenge that sends scientists straight into the lab, trying to figure out the absolute perfect recipe for creating energy. Okay, so to solve this puzzle, our first stop is profiling the candidates. Before you can make a good fuel, you've got to know exactly what you're working with, right down to the nitty-gritty. It's time to put this so-called waste under the microscope. So the very first thing scientists do is something called a proximate analysis. The easiest way to think about it is like a basic physical checkup for our potential fuel. It's step one to see if this stuff has what it takes. And this checkup looks at 4 vital signs. First up, moisture. Way too much water means you just waste a ton of energy boiling it off. Not good. Second, volatiles. Now these are the good guys, the flammable gases trapped inside. And when you're trying to make energy, more is definitely better. Third is fixed carbon. That's the solid, charcoal-like stuff that's left after those gases burn off. And finally, ash. That's the useless, powdery junk left at the very end. You want as little of that as possible. And hey, this isn't just a bunch of theory. You're looking at the real deal right here. Samples are weighed super carefully in these little ceramic bowls. They're called crucibles. And then they're popped into a special high-temperature furnace. By tracking the weight change as things heat up, scientists can figure out the exact amounts of those 4 vital signs.
So, what's the takeaway? We're looking for a star player here. The perfect biomass fuel is going to have a ton of that volatile matter, lots of gas, and super low moisture and ash. This simple checkup is a quick way for scientists to sift through different kinds of waste and find the ones that have the most promise. All right, after that basic checkup, it's time to go deeper. This next step is called the ultimate analysis, and a great way to think of it is as the fuel's DNA test. This is where we go beyond those 4 vital signs and map out the fundamental chemical building blocks, the carbon, hydrogen, nitrogen, and sulfur that make up the material itself.
And what's really cool is the machine that does all this heavy lifting. This is a CHN analyzer. You feed it a tiny, perfectly measured sample, and it just decodes that sample's core chemical signature. This info is absolutely critical for figuring out how much energy you can get and what kind of system you need to build to get it.
Okay, so we've profiled our candidates. We know what they're made of. Now it's time for the real stress test, the trial by fire. Let's see how these materials actually behave when we start to crank up the heat. And this is the star of the show for this part, the thermogravimetric analyzer, or TGA. Basically, it's a crazy accurate, high-tech oven that's hooked up to an incredibly sensitive scale. It heats up a sample at a perfectly controlled speed and records its weight second by second. So, what are we really looking for? What actually happens to a little piece of palm shell when you turn up the temperature inside that TGA? Well, the answer tells a really fascinating story about how things break down. All the data that comes out of that TGA gets turned into a graph. It's a curve that shows how the weight drops as the temperature rises. But it's not just a line on a page. It's a story. It's the narrative of that fuel coming apart. And it's a story told in 3 clear parts. So here's how it all plays out. Part 1, at fairly low temps, any water just evaporates. You see a little dip in the weight. Then comes Part 2, the main event. Around 260 degrees Celsius, things get interesting. The material starts breaking down fast, releasing all those awesome volatile gases, and that's when you see the weight just plummet. Finally, in Part 3, once you get above 600 degrees, the show's over. The weight flatlines because all you've got left is that solid char and ash. But here's a super important detail. How fast you heat it up matters a lot. Think about it like cooking. If you use slow heat, like baking something, you get a slower reaction, and you end up with more solid char.
But if you use fast heat, like broiling, you get a much quicker reaction that releases more of those valuable gases. And for making energy, we want the gas, so faster is usually better.
This leads us right to our next big step, unlocking the energy. See, knowing how it burns is one thing, but how much energy does it take just to get the whole process started?
And that brings us to this concept called activation energy. It's the bare minimum amount of energy you need to kickstart the whole chemical reaction. You can think of it like the key you need to unlock a door. Some doors have big, heavy keys that are tough to turn. Others have small keys that turn easily. Well, for a fuel, you want the smallest, easiest key you can find. A lower activation energy means it's easier to get the reaction going, which makes the whole thing more efficient.
And this whole idea of finding an easy key brings us to the grand finale of our investigation. Section 4, the perfect blend. This is where scientists stop being just analysts and start becoming master chefs, trying to create the absolute perfect recipe. So here's the million-dollar question. What happens if we don't just use the biomass waste by itself? Is there a way we can make that activation energy even lower by blending it with a little something else? Say coal? Could the mix actually be better than its individual parts?
And wow, the results, they speak for themselves. Take a look. On its own, the palm shell waste needs about 112 kilojoules per mole of energy to really get started. The coal? Pretty much the same, around 111. So you'd think if you mix them, the number would be somewhere in between, right? Makes sense. But get this, the blend with 40% coal, it only needs 81. That's not just a little better, that's a huge drop.
So the bottom line is, this specific blend is way easier to get going than either of its ingredients are alone. The two materials work together, they have a synergistic effect that just makes the whole process better. It's not just a simple blend, it's a super fuel.
And this is the magic number that all that science was pointing to, 40%. That is the sweet spot. That's the winning recipe that takes the least amount of energy to unlock the most power from our agricultural waste.
And that leaves us with a pretty powerful thought to chew on. We followed the science, we did the tests, and we found the perfect formula for palm shells. It really makes you wonder, with all the other agricultural waste out there, the rice husks, fruit bunches, corn stalks, what other amazing superfuels are just sitting there, waiting for us to find their winning formula?